Okay, let's go. So we've got this p-value which which we spent some considerable time developing, which is the probability. Well, there's quite a lot of meat on that. There's quite a lot of learning in that. There's quite a lot of concepts packed into this very simple answer here. This p-value here. So let's just remind ourselves what we're doing. We're looking at the probability, or we're looking for evidence that the home team is at an advantage. We've got some data, and we're now assessing whether or not that data is supporting our assertion that the home team has an advantage or not. And to some extent it looks as if it is, because 8 out of 10 victories is a lot more than you would expect, because you'd expect 5. But the more you think about it, the more confusing that gets, because even if the null hypothesis is true, and the null hypothesis is the negation of the effect we're looking for, I don't have a definition, I'll write it out again. Never hurts to write out definitions again. Fixes things in your mind. The null hypothesis is that the probability, even write legibly might help, probability of home win equals 1/2 exactly. And this is kind of a base case. And as I was explaining, the reason that we do it is not because it's interesting in itself, but because it's easy to calculate the consequences of. And in this case, if the probability of a home win is 1/2 exactly, we can run simulations and do d-binoms and all this lot and work out the probabilities of seeing various results that might have occurred, including the one that we observed. And observing that a scoreline of 9-1 or 10-0 would be even stronger evidence against our null hypothesis. See how we're trying to show that the null hypothesis is false. Is there evidence to show that the null hypothesis is false? And if that is the case, and your alternative hypothesis is true, which was, you'll remember, HA, which is that P was strictly greater than 1/2. If the alternative hypothesis is true, that means that there is a home team advantage. How do we think about the p-value that we've calculated? What we say is that the probability of getting this or more extreme is 5.5% of the time, which is quite small. But what you need, what people ask for, is not so much a precise calculation of the p-value. People want to know what it means. And so what we need to do is to find a cutoff value for that p-value that demarks, yes, there's evidence against the null hypothesis, or no, there is no evidence against the null hypothesis. So we'll need to think about how to assess this. The first observation is that the smaller the p is, the smaller the p-value is, the stronger against H null is. Small p-values goes to H naught, mean evidence against H naught. Why is that? As the p-value decreases, what you're saying is that if the null is true, you never see a scoreline of 8.2. If the p-value is very, very small, if the p-value is 1 in a million, what that's telling you is that these data sets here, these observations, never occur in the world in which the null hypothesis is true. So let me just write that down. P-value tiny implies that the data does not occur if the null hypothesis is false. Is true. So a tiny p-value says it's astronomically unlikely that we get this scoreline here of 8 out of 10 if the null hypothesis is true. And that is the same thing as evidence, oops, my pen's going here, against H naught. Small p-values are strong evidence against the null hypothesis. Okay, and the smaller the p-value, the stronger the evidence, because the less likely it is to get your data, or one more extreme, if the null hypothesis is true. So if p is very tiny, you can infer, this word comes up again and again and again. If p is tiny, we infer that h0 is false, because the data never occurs underneath the null hypothesis, and we've got the data's what it is, and so that tells us that the null is false. And the tinier, the smaller the p-value is, the stronger the evidence. Small p-values give strong evidence, and the smaller the p-value, the stronger the evidence, because the less likely it is to get your data in the world in which the null hypothesis is true. And so you say, well, I don't think the null is true because it's predicting that we get this incredibly unlikely result if p is very, very small. So you need a cutoff value for the p-value. Below this, you've got evidence against the null, and above this, no evidence, because it's consistent. So we need a cutoff value. And we usually choose, as I'm sure you'll know, we normally call it alpha equals 0.05 or 5%. So if the p-value is less than 0.05, we reject the null hypothesis because we've got evidence against it. Evidence to suggest h0 is incorrect. It's not proof that h0 is wrong. The null hypothesis could still be true because, as we've observed, if the null hypothesis is true, from time to time we get 8, from time to time we get 10, from time to time we get 9 and 10 values. We can only suggest that we've just got evidence. What happens if the p-value is greater than 0.05? You normally call it alpha, and I'll come back to alpha and beta later on. Then this means no evidence either way. P is greater than 0.05 means we haven't got enough evidence. We don't know. We've chosen our value, our cutoff value as 5%, and in subsequent weeks I'll talk a little bit about the choice of 5%, but we'll just leave it at 5% for the moment. If P is greater than 0.05, then there's no evidence either way. Observe carefully, we reject it. We never, ever, 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 ever accept a null hypothesis. And I'm saying that advisedly. Never, ever, ever accept a null hypothesis. We reject it, or we fail to reject it. So we either reject it or we have not enough evidence to reject h0. I can talk a little bit about this value of alpha. We talk about alpha as 0.05. We usually set this in advance. There's different schools of thought about this, and they're at each other's throats for sure. But we normally set alpha as 0.05. There's a problem with all this that, there's a problem here that if the null hypothesis is true, we reject it wrongly 5% of the time. So, of course we do, because the definition of p-value is the probability, if the null is true, of seeing our data, or one more extreme, or a data set more extreme. And if we choose a 5% cutoff, 5% of the time, we will reject our null hypothesis incorrectly when it's true. We commit an error 5% of the time. Because p is less than 5%, because your p-value is less than 5%, well, 5% of the time. Because that's how we set up the test. It's not entirely straightforward for discrete random variables, but we'll come to that later. This is called a type 1 error. Rejecting the null hypothesis when it's true. And if I go back to my R simulation here, we've got a world. I'll just go back to the simulation. There it is. In this world here, we've got 10 games. Probability of success, probability of a home win is 0.5. We reject it there and maybe elsewhere. There's no 9s in there unless I've missed them. We reject it about 5% of the time. Actually, we worked out the precise probability, which was 5.7%, was it? I can't remember what it was exactly. Oh, it was up here. It was up here. It's here, isn't it? It's the 5.4% of the time, not exactly 5%. Near 5% of the time. So, here, 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 and here, about 5% of the time, we reject the null hypothesis when it's true. And this is called a type 1 error. And of course, I only call it a type 1 error because there's a thing called a type 2 error. So I better talk about that. A type 2 error is the sort of converse of this. This is failing to reject H0 when it is false. If the null hypothesis is false, and we don't reject it, that's an error as well. It's not perhaps as serious as a type 1 error, but it's an error. You'll notice that in statistics we kind of minimize the impact of this kind of error by talking about failure to reject or not enough evidence. Doesn't matter how you sugarcoat it. Somebody said, is there evidence against this null hypothesis? And you said, no, there isn't. That is a mistake. That is your data being misleading, or your data not playing ball, or your data not being useful. So it's kind of a converse. It's failing to reject the null hypothesis when it's false, and a type 1 error is rejecting it when it's true. Now, of course, in proper scientific work, you won't know if it's a type 1 error or a type 2 error you should be worried about, because you don't know if the null hypothesis is true or the null hypothesis is false. So you don't know which one of these you should be bothered about. A type 2 error. So we need some quantification on this. We talk about the probability of a type 1 error equals alpha. That's the first Greek letter in the alphabet. And we normally set alpha equal to this 5% here. The probability of a type 2 error equals beta. And you want these to be small. Alpha and beta to be small. Why? Because they're different types of screw-ups, and you don't want to screw up. We'll see later on in the course that if you've got lots and lots of data, you can make these very small values indeed. And if you don't have a large amount of data, then you are doomed to having large probabilities of error. So we want alpha and beta to be small. So I'm going to spend a little bit of time talking about that. I don't think I'll have time to cover the Gaussian distribution today like I thought I would, but never mind. Cover that next week. We can make alpha equals 0. How do we do that? Well, alpha equals the probability of a type 1 error equals the probability of rejecting it just incidentally observe, I'm getting my thoughts together on null hypotheses and type 1 errors and type 2 errors. I write it out again and again and again. Doesn't hurt, just write it out. You're doing so now because you're sort of copying what I'm doing, but I want you to get into the habit of writing out the definitions and just making sure you understand it. Okay? We can make this 0, can force, alpha equals 0. How can we do that? Can anybody say how we can do that, just in words? By never rejecting it, irrespective of the data. So that is a stupid thing. Well, it's not stupid. Well, it's perfectly sensible. If somebody comes up to me and says, don't make a type 1 error, yes, sir. I work in statistical consultancy, and quite often people come to me with sort of demands. And they say, I don't want screw-ups. And you say, yep, sure, I can arrange that. My alpha equals 0. He wants alpha equals 0. And I can say, yes, I can do that. But the only way of doing it is never having the possibility of doing it. So I'll never reject it. And if I never reject it, that means I'm ignoring the data. Which is stupid. So you can't deal with alpha in isolation. Of course, what happens to beta? Beta is the probability of failing to reject it. The probability of failing to reject it when it's true. When it's false. So beta equals 1. Why? Because I never reject it. So I can't screw up in the second way. I can't commit a type 2 error. Because type 2 error is failing to reject it. And if I never reject it, I can never make that type of error. So alpha equals 0 means that beta equals 1. So yes, I can control it, but it bites you on the arse because you've got a beta equals 1 here. So you've taken all your error and taken it away from here and dumped it onto here. And of course, I can force, let's write it out here, I can force beta equals 0. How do I do that? Well, a type 2 error, beta equals the probability of a type 2 error. Yeah. Failing to reject it when it's false. When false. So how do I get that? How do I get beta equals 0? How can I suppress all type beta errors?
By always rejecting it?
Indeed. Can do this. Always rejecting it. Which is stupid. Because somebody comes up to me and says, I've got some data, and I say, right, reject it. And they say, let me show you. No, I'm going to reject it. You're ignoring the data. So beta equals 0 forces alpha to equal 1. So if we take this absurd, it's possible, but it's stupid. It means you're not honouring your data. It seems to me that you should have some kind of parity between alpha and beta, but that's not the way it works. You'll notice that what we normally do in statistics, so we want alpha and beta to be small. alpha and beta to be small. Can't do this in general. So we compromise as follows. We set alpha equals 5%. That's your cutoff for your p-value. And we worry about beta separately. This is not a mathematical statement. This is a statement about early 21st century Western society. It's because people are hung up about type 1 errors, and for reasons that are not clear to me, people don't seem to be that bothered about type 2 errors. People are much more worried about rejecting a true hypothesis than they are about failing to reject an incorrect one. So the way I tend to think about it is, in a legal context, it doesn't quite work, this. It doesn't quite work. It's not quite right. Your null hypothesis is that your suspect, in a legal context, your suspect is innocent. Your alternative is that he's guilty, or she is guilty. I've got to stop myself from using gender inappropriate language here. It's very difficult. Okay? So what do your type 1 errors and type 2 errors look like here? Okay, so type 1 error is rejecting when H0 is true, equals, what do you call it, condemning, or you say somebody's guilty, convicting. Convicting an innocent person. A type 2 error is failing to reject H0 when it's false. Equals letting a guilty person go free. What do you call that? Letting somebody go free? It's not convicting. What do you call it in legal? Exonerating. Finding guilty person or not guilty and letting him off. But of course, in any I can talk about probabilities and alphas and betas. In a specific court case, you've got some person who's suspected of committing a crime. You don't know whether you should be worried about type 1 or type 2 because you don't know for sure if that person really is innocent or really is guilty. And it's a matter, certainly, and I think correctly, it's a societal matter to see how worried are we about this and how worried are we about that. You'll notice that I'm taking the null hypothesis that the suspect is innocent here. So what you ask yourself, what is the probability of convicting an innocent person? And so there's certain standards of evidence, and you normally talk about the burden of proof and innocent until proven guilty and all of this. However, you need to have a balance between type 1 error and type 2 error, and that balance is correctly a matter for society to decide, not for statisticians. So people ask me, why 5%? And I say, well, it seems to work and my clients seem to be happy and nobody gives me a kicking if I use 5%. So I use 5% to keep out of trouble. But it is fundamentally arbitrary and it is a social decision, not a mathematical one. That 5% seems to be a value that people are happy with and it doesn't impact too badly upon beta. I can make it smaller. I can make it 1%, and people sometimes do say 1%, but that gives me a higher probability of beta. It gives me a higher probability of a type 2 error. Okay? So today we've covered p-values, we've covered the binomial distribution just as way of revision, we've covered p-values, we've covered null hypotheses, and we've covered type 1 and type 2 errors. Probabilities of committing those are alpha and beta respectively. We usually control alpha and specify alpha as 5%, purely for mathematical convenience. Where does 5% come from? Well, I've just pulled it out of my head because that's the conventional value. It's got no meaning It's just a value that we all agree upon.
Everybody said, okay, that sounds good.
Yeah, basically. I could make a case for 4.7%, but there you go. And I can make a case for 5.1%, but there you go. 5% is about right. Okay, I'm going to stop there. Thank you.